And for today, we are going to continue 5.3 aerodynamic design, okay, which we will look into the aspect of blade element considerations. Okay. With regard to blade element considerations, so last Monday you have already been introduced about propeller, what are the nomenclature of propellers, the aspect of different type of propeller characteristics and so on. And to continue from our last Monday topic, we are going to talk on blade element consideration. So basically the blade element theory is somewhat similar to wing theory. So in this particular theory, okay, the blade is divided into small sections which are handled independently from each other. If you already learn aircraft structure, there is a wing theory topic. It is quite similar, okay, to the one that we are going to go through today. So each segment has a chord, a blade angle, and associated airfoil characteristics. These isolated airfoil assumptions is found to be substantially correct for any 2 or 3 bladed propellers, except near the hub section. So at any given radius, we are going to look at the figure 4.37 later on. At any given radius of the propeller, the circumferential distance between 2 successive blades is called spacing. Right? So we have the radius of the propeller, distance between blades. For example, you have 2 bladed or 3 bladed, we call it as spacing. And while the length of the blade section between the leading and trailing edge is called the chord. And let us just quickly look at the picture here, figure 4.37, right? So imagine you have this 3-bladed propeller, so it has a radius r, okay, and we will the cross section, between the leading edge and the trailing edge is called the chord, and the chord of the blade. Since the spacing, okay, spacing in this particular example is spacing between one blade to the other blade, okay, so right, since the spacing over the chord and the chord of the propeller blade for 2 or 3 bladed propellers are much greater than unity, so this justifies the use of isolated airfoil characteristic in this particular theory. So multi-blade propellers for more than 2 and 3 number of blades, for which the ratio of S over C, the spacing over the chord, has fallen to a value of order 1 or less, will have to be treated as cascades. Okay, so we will refer to this particular figure from now on. There are explanation with regards to figure 4.37a as well as 4.37b. Right, the forces acting on a small section of the blade, we are considering only a small section of the blade, for example, like this particular region, we have a cross section there, okay, we cut it cross, and which are determine the lift and drag, where we can determine the small forces acting on the small section, where lift and drag are determined, and then integrated over the propeller radius in order to predict the thrust, because we want to find out what are the thrusts associated with the blade, the thrust, the torque, as well as the power characteristic produced by the propeller. Okay, so the forces acting on a small section of the blade, okay, the forces which is the lift and the drag force, are first determined. and next resolve into two perpendicular components in the axial and tangential directions, and finally integrated over the propeller radius in order to predict the thrust, the torque and power characteristics of the propeller. So if we look here for figure A, a differential blade element of chord C with dr, okay, the with dr, so it's just a small portion of the radius located at a radius r from the propeller axis. Okay, so if we just quickly go back there, we imagine there's the radius of the propeller. This is the small element that we are considering, and we take it out into figure 4.37a, where we have the components of the lift, right, and the drag. L is lift, D is the drag. Okay, the element is shown acting under the influence of the rotational velocity. The symbol is this, and this is the rotational velocity, V having a cap there, Vt, as well as the forward velocity, V prime with an arrow pointing to the right, and this is the forward velocity, okay, and the induced velocity symbol W cap. Okay, so V, capital V cap, subscript T is the rotational velocity. Forward velocity is V prime with the arrow, and then the induced velocity denoted by the symbol W cap. The resultant or relative velocity, the capital V subscript R, that is resultant, R is resultant, okay, and having the cap there is can be expressed in this equation 462. Okay, so the resultant or relative velocity V cap R equal to the forward velocity component, right, plus the rotational velocity as well as the induced velocity. Right. The axial velocity and rotational velocities are already given over here, right? It is being expressed as equation 463 and equation 464, right? We have a new component over there, new item over there. The relative fluid velocity varies from hub to tip, primarily under the influence of the rotational velocity component, omega r, and the inflow factor. We have already introduced inflow factor before in last Monday lecture. Okay, and looking back at figure 3.7, it shows the velocities and forces on the blade element that lies between radial station R, it is just a arbitrary location R, and location R plus dr, the radius plus a small increment of the radius, and whose local chord is denoted by C, the chord is there, and the section has a geometric pitch angle, or we call it as the blade angle, okay, where beta equal to alpha plus pi, right? So with the alpha is the local two-dimensional incident angle or the angle of attack, okay, and pi is the advance angle given by the expression 4.66 over here. Let us just quickly go back to here, where you want to see the where is actually the angle of attack. It is this is alpha, this is beta, and pi is actually the direction of the W component, the induced velocity. All right. Okay, so we can express the in the pi advance angle in term of the inflow factor, the angular velocity, okay, in equation 466, and we can then define the dimensionless radius x, which is equal to the radius r over the big R, then you can get this expression, right? 4.67. We have now introduced more symbol over there. This time is J, okay? So the blade angle beta is calculated from the advance of propeller during one revolution, known as the geometric pitch, P, as follows. So tangent beta, the blade angle, equal to the geometric pitch over pi d, okay? And the radial pitch distribution will be specified for a given blade, but for a representative pitch is quoted at reference radius conventionally taken at either 70 or 75% radius. Overall solid body pitch may be varied by rotation of the blade about its radial axis. Okay, let us look into more detail how to calculate the thrust and torque using the blade element consideration. We move into 5.3.3.1 with regard to the thrust and the torque. Okay, so we are still referring to figure 4.37. Later on, we are going to show again the figure. The axial and tangential forces acting on a blade element generate the thrust, delta T, the thrust, the small change of thrust, and the torque itself, small change of torque, okay? Contributions of the blade elements and can now be written as expression 469 and 470, right? There's a lot of equations in this particular subject. And the small changes of the lift and the drag, delta L and delta delta D, are the lift and drag forces on the blade element. Okay, introducing the definitions for lift and drag coefficients, we have CL and CD, as well as the dynamic pressure Q, and the symbol used here is Q. Then the lift and drag forces per unit span length, the L and D, can be expressed for respective component. For the coefficient of lift, CL, equal to this term. Coefficient of drag is denoted by this term. And the dynamic pressure, half rho V squared. Okay, this is going to be your equation 471, right? And moreover, from figure 437b, the relative velocity VR is given by equation 472, right? And we can then introduce relations between 471, 472 equation into equation 469 and 470 that we have already shared in the previous slides. And we want to assume the number of blades is B. We get the following relations for the thrust. Okay, this is the relation for the thrust, and then the torque gradients. Okay, so 473 and 474. So with the non-dimensionless value x equal to r over r, the local solidity sigma r at station r is defined as this expression. Okay, and the solidity at the propeller tip can also be written. This is at location radius r, small r, at the full length of the radius of the propeller, the capital R, can be written as this expression, 4.75 B. In the succeeding equations, the thrust force is non-dimensionalized by the rho n squared d to the power of 4 to obtain the coefficient equation 459A, and the torque will be non-dimensionalized. All right. So that resulted to this. The power of take note on the power of the D there is become 5, and to get the torque coefficient CQ, and we can see equation 460A. Introducing them into equation 473 and 474, you get this expression. We are not going to further elaborate on this equation. There's a lot of equation, but later on when we go to the example, you may realize that, okay, this equation can be applied here and there. Okay, and the relation between the drag and the lift forces on blade element is given by tangent. We call this the E, eta, L over D, or CL over CD, coefficient of lift over coefficient of drag. And introducing equation 477 into 476A and 476B, you get expression 478. And this is how it is being derived, okay? And also 479. And by integrating equation 478 and 479 to obtain the thrust and the torque, which is Q, coefficient of torque over there, you can use expression 479. Right. Let us move into propulsive efficiency. Don't worry about the equation that we introduced for the thrust, for the torque, for the coefficient of lift, drag, as well as coefficient of torque. So we will look into the examples later on. Now we move into propulsive efficiency. Okay, the propulsive efficiency using the blade element is defined as the ratio between useful work, the velocity times the a small change in the thrust, delta T, to the supplied torque power, okay, the rotational angular velocity times the small change in the torque. Okay, so you can have that propulsive efficiency BE, basically zeta blade element, right, in terms of the useful work, V delta T over omega delta Q. So looking back at figure 437B, the blade element theory, okay, from equation 467, 46 as well as 472, as well as the figure, this particular figure, so we get the expression to be rearranged. The expression for blade element efficiency, zeta BE, okay, we can rearrange all the equation back to be simplified to equation 480. Right? So the local propeller efficiency can be seen to be dependent on the angle. Eta equal to this expression, tangent CD over CL, and the interface factors, inflow factor A and A times the angular velocity omega. All right. And figure 4.38 over here illustrate the variation of blade element efficient as a function of the advance angle and the angle eta just now. Okay. So in this particular case, a variation of blade element versus the angle, you can see here at location pi equal to 45 degrees, right? Minus eta over 2, and we have that, and the in terms of the efficiency, efficiency using the blade element theory. Okay, so we can see here CL over CD, okay, is increasing by we can see for this one is basically when the angle eta equal to 0, okay, and then this is when CL over CD equal to 50, and this is the plot when CL over CD equal to 10, right? So that is the variation of blade angle element versus the advanced angle pi. The following two cases are identified when the efficiency of the blade element equal to 100%. And this is a straight line case when eta equal to the inflow factor A, okay, which is equal to inflow factor A subscript angular velocity omega equal to 0, right? And then for when the case of the efficiency of the blade element is variable, where in this case eta equal to not equal to 0, the A also not equal to 0, A omega subscript omega also not equal to 0, and the efficiency has 0 value when angular advanced angle equal to 0 and advanced angle equal to 90 degree minus the eta angle. Okay. At an in-between value, the blade element efficiency acquires a maximum value, which can be obtained in between 0 and the maximum, right? We can obtain it by differentiating equation 4AT with respect to the pi and equating the differential to 0. And then we can have this expression, and several curves are obtained for different drag to lift coefficient. Right. Let us move into dimensionless parameters. We have examples in this dimensionless parameters subtopic. Okay. There are actually 9 independent variables needed to define the performance of fixed pitch propeller in subsonic flight, namely the thrust force, okay, the T, and the torque Q, the power P, air density rho, the compressibility beta, and then we have the mu, air viscosity, propeller diameter D, and then the approach velocity of speed V, and the rotational speed N, expressed by variables between bracket. From all these 9 variables, independent variables, there are basically 3 fundamental units of mass M, length L, and time T. Using dimensional analysis, we get 6 basically dimensionless group from these 3 fundamental unit. Okay, 9 minus 3, you can get basically 6 dimensionless group parameters. Right. The first dimensionless parameters associated for this topic is thrust coefficient. All right, CT. Okay, which is can be expressed the thrust coefficient or TC, CT or TC. Okay, it can be expressed in terms of the thrust itself over the density over n to the power of 2 and diameter to the power of 4. At the same time, we have torque coefficient. Okay, so CQ torque coefficient equal to the torque value itself over rho n squared d to the power of 5. Okay, so that will be equation 481 and equation 482. Let us move into the next dimensionless parameter, which is the power coefficient, CP. Right, the CP itself is equal to the power over rho n to the power of 3 d to the power of 5. So a relation between power and torque coefficients can be derived as follows. So we combine the torque coefficient as well as the power coefficient. You can get the CP itself equal to 2 pi CQ. So combining equation for power coefficient and the torque coefficient, you get the relationship between the two. And then the fourth dimensionless parameter is the advance ratio or the speed coefficient, J, which we introduced in the earlier equation, right? J equal to the speed over ND. And then we also have the Reynolds number as well as the Mach number. All right. So those are the 6 dimensionless parameters associated to the topic on the propellers. The first 4 dimensionless quantities are correlated by the following relation in terms of coefficient of torque, coefficient of thrust, coefficient of torque, CQ, and another important dimensionless quantity is the speed power coefficient, CS. Sometimes it is called the CPS, right? So can also be expressed in terms of the power, the speed, the density, and the n to the power of 2. Or it can also be rearranged in terms of J at the same time. As notice from equation 4.86, the speed power coefficient eliminates the propeller diameter. Now back to equation 455A, 455C, and using equation 481, we can express the factors A and B by the relation, right? So you can rearrange that to get equation 487. The actual propulsive efficiency can be expressed in terms of the thrust and power coefficients. Equation 481 and 483b as follows. So you can put down all the parameters over here, right? So the propulsive efficiency zeta P, okay, propulsive efficiency can be expressed as JCT over Cp. As discussed earlier, the maximum value of ideal crude efficiency and zeta F is actually 100%, while the peak or actual propulsive efficiency equation 488 is normally less than this value. All right. So why is that? This is due to the ignored losses in the ideal actuator disk model arising from the following points. One is that rotational flow or the whirl about the rotor axis in the wake. Okay. And then the second factor is that profile drag or viscous friction and the form drag of the flow over the propeller blades, which is near the high speed zero thrust condition. Profile drag is dominant. And then the third factor is that interference effects in the hub region between multiple blades as well as the nacelle. And then compressibility effect about shock wave and shock boundary layer interaction. And finally, the factors on lateral components of incoming flow that occur when a propeller is yaw. All right. So these are the reason why the actual propulsive efficiency is far less than the ideal fluid efficiency. Two other important parameters which are relevant to propeller power are actually the power loading and the activity factor. We can then first look at power loading, PL, right? The expression for power loading is given over here, equation 489, and the activity factor, AF. So is also being expressed over here, equation 490. Bear in mind that both of these are a measure of power absorption by the propeller and are used to compare the performance of different propeller design. So that's the reason why certain propellers being designed just having no it's just simple straight propeller. There are propellers having simple twists, a half twist, and there are propellers being designed in such way it has multiple twists. Okay, so the PL is a simple disloading, whereas the activity factor AF is designed to express the capacity of the blade to absorb power. Okay, and of course the activity factor AF is dimensionless with a value of around 80 per blade. Let us look into one example. Hope that you can appreciate all those equations that we have already introduced earlier. All right. So right after example 4.6, we can have a short break. Okay. In this example, it is required to design a three-bladed propeller having the following data. Given the power is 260 kilowatt, we have rotational speed of 2,500 RPM, flight speed V equal to 300 km per hour, the tip Mach number is 0.8, and the sonic speed is 340 meter per second. So the rotational induction factor, A omega, is assumed to be constant and given as 0.001, and this is not zero ratio to 001. This is 0.001. Sorry for the mistake there. Okay, other data given in the following table, and using blade element theory, R over capital R, C over R, the CD, coefficient of drag, and then this is for the three blades, DT over dr. Okay, so it is given at location 0.2, 0.4, 0.6, 0.75, and 0.9. So what is you required to calculate? You have to calculate the radius of the propeller. What is the radius of the propeller? Capital R, right? And then the propeller efficiency, number 2. And then number 3, at each blade section, right? So blade section over here at every location here, 0.2, 0.4 until 0.9. Okay, you have to calculate axial interference factor A, lift coefficient, angle of attack, alpha, blade angle beta, and local propeller efficiency. So it's actually a huge task to calculate everything for the section. Basically, it's just a repetition. Okay. As a hint, for calculating the angle of attack, we can use one of the following relations. The angle of attack alpha, okay, equal to CL over 2 pi for MW, Mach number at the tip, equal to 0.3 minus, between 0.3 to 0.6. Okay, so or you can use this other expression for Mach number value around 0.7 to 0.9. So in our case, okay, the tip Mach number is 0.8. So that's why we are going to use the second set of expression for calculating the angle of attack, alpha. Right. The first item need to be calculated, which is the radius of the propeller. So relative velocity at blade tip is calculated from the relation. We have the relative velocity Wt equal to the Mach number at the tip times A. Okay, you have 0.8 times 340 already given earlier, so you get 272 meter per second. So since Wt is in this relation, okay, which is equal to 272, and the speed V equal to 300, we want to convert it into meter per second. Just now it's 300 kilometer per hour, so convert into meter per second, 83.3 meter per second. Then you can then find the velocity, ut equal to the square root W squared t minus V squared, you will get UT equal to 258.5 meter per second. So using the earlier expression, UT equal to 2 pi n time R, right? So you put all the values there, rearranging for R, you will get the radius of the propeller R to become 1 meter. Okay, so try at your own sweet time to go through this example and make sure you can get R equal to 1 meter. Okay, moving into the propeller efficiency. The thrust is obtained from the rate of thrust distribution along the blades as follows. So you use this expression T, and then you can get thrust equal to the 2649.7 Newton. All right. And the propeller efficiency itself is calculated from the relation. So just to note here, this is at for different location on the propeller itself. So you can have the first, second, third, and fourth and fifth. So you can try to go through and get whether you get the value. And this is for dt over dr, for the 3 blades element times the small change of dr. Okay. The propeller efficiency is calculated from the relation, okay, zeta p equal to t v over p. We already obtained the thrust value. We have the velocity in meter per second. We have the power given, okay, 260 60,000, and the zeta p can be calculated as 84.86%. Okay. Going into the third question in this example, element of thrust force over a blade element at radius r and thickness dr is given as follows, right? So and we can then use the expression for 2a over here, okay, and to continue from the above equation, we can calculate a at each blade section. For blade section 0.4, you put the value of 0.4 in the equation. You can get the advanced angle, pi to be 40.04 degree, okay, and then from equation 473, right, so you take up for equation 473 using the coefficient of lift expression as well with, okay, expression for q, the torque equal to rho v squared over 2, you can get the torque to become 4,250 Pascal. Putting into expression for the coefficient of lift, you get it to be 0.6665, and then you have the W expression, you get 133.8 meter per second, and then you can get the using the expression for the Mach number. Mach number at the tip is equal to the 0.394. So since it is less than 0.7, okay, so we use the expression for alpha, the first expression, CL over 2 pi, simplified version, okay, and then you get alpha to become 6.08 degrees. You can immediately get the beta 46.08 degrees, and then you can get the angle eta to become 3.4344, and we can get the value for the pi plus eta equal to 43.4344 degrees. So the efficiency for the blade element okay, can be found as 83.97%. Right. So if you can continue on yourself, right, repeating the above procedure for the different section. Just now we only calculate for 0.4. You can continue for 0.2, 0.6, 0.75, as well as 0.9. Try to get the answer and compare it against the value obtained here in table 4.8. Right, I think that is the best time for us to stop first, and we can have our short break.